Hey guys, welcome to this video about terrain. In this video, we'll be going over how to import satellite data into Houdini and your game engine of choice. In this day and age, where games keep getting bigger, terrain often takes up an incredible amount of time. But using real-life data, we can quickly set up either a prototype or a final look in terrain based on any data you can find. So without further ado, let's get some high data into Houdini and make it work. One place where you can find this high data is opentopography.org. Once you're on the website, you just go to data and raster. You'll be met with a whole bunch of different sources. For our purposes, we'll be using the global data though, and I'll be picking from the SRTM global 30 meters one. Once you're in there, you can just select a region by using this button here. So let's say we want to have an area in Switzerland. We can just select it like this. Now, for validating your terrain, I personally recommend keeping in mind the shape of this rectangle here and copy these two. We'll be needing the coordinates later on, and the area, again, is just a nice validation tool to make sure that your terrain is the right size. So I just paste these in here usually, and if you fill in a job title and your email address, you can just submit it and then download the map. I already have mine downloaded though, so let's jump into Houdini and get some terrain in there. So in Houdini, I've put down a geometry node, and let's get ourselves a height field file to import our file. So just browse to your directory. Let's see, there we go. And right off the bat, you can see it doesn't look too great yet. It's missing some height information. It's flat as a pancake, but also it isn't the right size yet. First thing we'll have to do to fix that is set our sizing method to grid spacing and set the grid spacing to 30 meters after the name of our shuttle mission. With that, we're going to have to set our height scale to something as well. This is a very specific number, and it is 65,536. If you want to know more about this number, I'd recommend watching the Side Effects Terrain webinar, which is linked in the video description, which will explain a bit more about why we do this and, a bit more information about that. Now, looking at this terrain, you might see that it doesn't fit the shape of your rectangle selection. And if I were to, for instance, put down an attribute wrangle to measure this thing, setting it to detail and fetching the size. So I'm going to get a size vector. I'm going to just do size equals get bounding box size of input 0, which is the first input. And I'm just going to say f at area equals size.x times size.z. And I'm going to divide this area value by 1,000,000. Because the Houdini does everything in meters, and we want to convert it to kilometers for now. So that should be good. I'm going to open up my geometry spreadsheet, which is on the bottom left for me. And as you can see, our area is 156 square kilometers. Now, I have my reference open here, and it says that it's supposed to be a bit smaller than that. It's supposed to be 116 square kilometers. So that doesn't sound right, does it? And the reason for that is Houdini has no clue how to interpret an image from a spherical source and map it onto a flat plane, which is also a UVing issue, of course. But in this case, we can fix it by using a formula called the Haversine formula, or Haversine formula, which you can see on screen now. Now, for our purposes, you won't need to actually understand this formula. We're just going to be copying it into code and using it to create some proper dimensions for our terrain. So let's put down a Python node and create this formula. So to start off, I usually remove these two comments and press a couple of enters. So the first thing I'm going to do is import the math module as m. And I'm going to create a radius variable, which is equal to the Earth's radius in kilometers. So that's 6,371. I'm going to put .0 behind that to make sure that it's a floating value. And we're going to define a couple of functions. So to start off, I'm going to create a have function, which will take a delta variable and return the powered sign. So we're going to do 2 multipliers here and then do a 2. This is of course equal to a power in Python. And then we're going to take our input value and multiply it by 0.5. There we go. And then next up, we're going to create our actual haversign function, which will take 2 values, 2 coordinate values, that is. First of all, let's unpack our coordinates using just this method here. Since these coordinates will hold 2 values, we can just unpack them right into these 2 variables here. And we can do the same for our coordinate 2. So I'm just going to copy paste these and replace these with 2's. When you're copy pasting, of course, watch out with pasting and adjusting these numbers, because if you have large swaths of code, then you might forget something and break your code later on. Next up, I'm going to convert the latitude values into radians for use later, because the longitude and latitude coordinates are degrees rather. So we'll need to convert them to use them properly with Houdini's functions. Next up, I'm going to create my delta variables. So delta latitude is going to be equal to the radians of the second latitude minus the first latitude. Keep doing those semicolons, as of course is something that Vex uses. And then I'm going to use the longitude, the exact same formula, except for the longitude. With that, we can get started on the actual formula. So let's let h be equal to the half of delta latitude plus the cosine of the first radian latitude multiplied with the cosine of the second radian latitude, finally multiplied with the half of delta longitude. This value in turn is going to be multiplied by 2 after it's been made into an arctangent. Now, as the formula might imply, we should be using the sine function, as the name haversign implies. But according to the article, you can also use the arctangent function. Now, there's some more information about what the differences are between the sine and arctangent function in this space, and why you could use one or the other, but I'll leave that to you. I'll leave a couple of links in the description if you want to read up on this. And finalizing this formula, there we go. Now we need to multiply this with our radius, since this formula will just calculate the distance on a sphere, and since the Earth is spheroid, we can just multiply the radius by the c value. Let's make sure to put an equals here to make sure that it doesn't break. And there we go. If we click out of the Python node, we can validate that nothing in this code breaks as of yet. Now we need to actually import our coordinates. So let's edit parameter interface and create a string parameter for ourselves. I'm going to call it coordinates. And in Python, I'm just going to create a variable called parm, and I'm going to import this coordinates parameter. So as it said here, it's called coordinates, and I just typed coordinates here. Now I'm going to copy my coordinates into that parameter. There we go. And if we print this parm value, and we visualize the node, oh, looks like we broke something. Let's middle mouse click to see what's going on. Ah, I should have added a little column there. There we go. And as you can see, we have ourselves the coordinates printed. Next up, we'll need to separate these into individual values and convert them to floats. Now, the way we can do this is create a parm split variable and use the split function. So you just do dot split, and add a little space in here. Now the reason I'm making this a space is because, of course, I'm using, whoops, let's remove this print statement or comment it out at least. So the reason I'm using spaces is because right here I'm using spaces as well. So keep that in mind. You can replace these with dashes, underscores, commas, dots. Doesn't matter as long as you replace them in here as well. Once we've split our parameter into 4 values, which we again can validate by doing another print, parm split in this case. Here we go. You can see that I have 4 different values now in a list. But we don't want to have them be strings, we want to have them be floats. And we can do this with a inline for loop, which works a little something like this. For x in parm underscore split. Now Python will just happily let you override this parameter from a string to float, so do be sure to validate that you actually convert it to float, because Python will let you do this and it can be dangerous sometimes. And if you print it now, you can see that we have a couple of float values here. Now this inline for loop is roughly the same as what I'm about to write down now. So output equals for x in parm underscore split, and then output dot append the float of x. Not only is this a lot shorter and cleaner than this 3 or 4 line thing here, it's also faster. So if you have to do some things with lists like this, I'd recommend using one of these. So with our float values at the ready, let's convert these into coordinates that we can input in our formula. So to start off, I'm going to create coordinate 1a, coordinate 2a, and a couple of backspaces there, coordinate 1b, and coordinate 2b. The reason we're creating 2 coordinate sets is because we want to have 2 lines and not 1 diagonal line. So let the first one be equal to a list that is made up out of parm underscore split the first index and the second index. For the second one, we'll be using the first index here, and then the second or the third one here, so 2. And we'll be keeping the y value the same, because we only want to have the difference of the x value. Now we can just copy this thing here and paste it here and here. And in this case, we're going to only change the y value. So we're going to have 1 here and then 3 here. So altogether you should have 1, 1, or 0, 1, 2, 1. And for the b coordinates, 0, 1, 0, 3. Now let's plug these into our formula. So I'm going to just say a equals Haver sign, coordinate 1a, coordinate 2a, and we can copy this whole lot and just paste it to do the same for b. We'll only need to change these to b. And we can start printing this to make sure that we actually have some output. So let's print, first of all, a tuple of a and b. And for good measure, I'm also going to print a times b, again divided by 1,000,000 to convert, or no, we don't have to convert to kilometers because it's already in kilometers. And there we go, we have 115.6 square kilometers, which is roughly equal to 116 square kilometers if you round it up. So we've successfully created the dimensions of our terrain. Now let's export these onto a couple of attributes to port them onto our geometry. For that, I'm going to create a add node and add a single point. So just hit the check mark here. We're going to add a attribute create. And we'll be adding 2 attributes. So I'm just going to connect all these nodes here. I'm going to first of all create an X attribute, set it to detail and float of type. And then another one, we're going to call this one Z, again, set it to detail. And once we're in here, we can use the geometry that Houdini has provided for us. So node.geometry. We can use that using the set global attrib value. That is not caps. And we're going to set x to be equal to a. And we're going to do the same function for our z-axis. And there we go. If we look in our geometry spreadsheet again, we should see that we have two new detail attributes set to our values here. So now we can actually start creating our terrain. So what I'm going to do is create a grid, place it down, and import our detail attributes using a detail function. For that, we're going to have to reference our Python node. Let's actually call this something useful like distances or axes. That sounds fun. So I'm going to reference the axes node. We're going to query the x variable, or the x attribute of index 0. Do this again for the second one, set this to z. And now we have our grid. But this time it's way too small. We're going to have to multiply this by 1,000 because again, Houdini does operate in meters. Now you can multiply it right here in the grid, or you can multiply it here when you're defining your attributes. Either one is fine. I just did it in the grid this time. Now we're going to set our rows and columns to be equal to the resolution of our height field file here. So what that means is I'm going to say copy the parameter of this grid spacing thing, paste it into the rows and into the columns. Here we go. I'm going to add, so I'm going to take the size, I'm going to copy parameters for the second value, and I'm going to paste it in here. So now we have 2, and I'm going to divide that size by the grid spacing. So now we have our grid spacing on the z-axis. I'm going to do the same for the x-axis. Paste it again, make it a division, and there we go. So now we have nice squares again. With this, we can use a attribute from map to import our map. We're going to have to do a couple of things to this thing. First of all, I'm going to set the export attribute to be height, and I'm going to set the type here to float. In here, we don't need to change anything. And for the map, again, I'm going to use my height fit map. If we go into our geometry spreadsheet, we should see that we have a nice 0 to 1 attribute here. And again, we're going to have to actually set the scale here to the number we used before. So 65,536. Never mind. We don't have to set the scale. We have to do that later on. All right, so this works now. Let's displace our points using a point wrangle. Just going to plug that in here. And I'm going to use set our y value of our points to be equal to the height the height attribute we just created. Again, we're with the same problem that it's not high at all, so I'm going to just multiply this by this value here. And there we go, we have our terrain. For good measure, I'm just going to pull it down. I'm going to use a transform. Let me just transform it down to make sure that it is stuck to the ground using the ymin, $ymin. So if you subtract that, it subtracts the bottom, which puts it on flat on the ground plane. There we go. So now we can get a height field, and we can actually copy our things here. So I'm just going to copy that detail attribute, paste it into our size. Do the same for the Z. And again, set my grid spacing at 30. And here we go. We have our height field. We have our actual height. We're going to use a height field project to transfer our data. Be sure to watch out with this height field project because it actually has a distance limit. And as you can see, our terrain is apparently way higher than this distance limit. So I'm just going to set this to, let's say, 10,000. And that will work for now. You can play with this value to make it as high as you need to. This works for us. So we've imported our terrain into a height field. Let's start adding some detail, because if we zoom in, I'm going to close my geometry spreadsheet here. If we zoom in, you can see that it's not very high detail. It only has 1 pixel per 30 meters, so that's to be expected. The first thing we have to do to increase our detail is use a resample node, a height field resample to be more exact. Using this node, we can increase the scale, or we can specify an exact resolution. For instance, by axes, which will give us a exact size. We're just going to use the multiplier though. I'm going to multiply it by 3 in our case, because I think that seems to work well. Keep in mind though, this resolution scale is going to be exponential on your resolution. So beforehand, we had a terrain that had a size of 336 by 382 voxels. Now, after the resample, that has tripled, or rather, it has been multiplied by 9 times. So the resolution is 1008 by 1146. So both axes have tripled, which means the total amount of voxels has multiplied by 9. Keep this in mind if you're scaling, because it will really slow down the operations on the other height field nodes. That being said though, let's get back some of our detail. Let's make these peaks here, these ridges, a little bit more crisp. And we can do that using a distort node, or rather the distort by layer. This node will let you displace your terrain by its gradient, which means that every pixel on the terrain will move to the direction of the pixel that is next to it that is higher. So if we look at it from the top, we have this river here, and we have this tall ridge here. The river will try to move towards this ridge. Right now though, it only displaces it by 1. Let's make this something drastic to really see the effect. I'm going to make it 30. And as you can see, it's kind of like shrink wrap. It really makes these ridges very tight, though this value here is way too high, so I'm going to set it to something a bit lower, like 10. I think that looks nice. If you disable the node by pressing this little yellow thing, you can really see the difference. You can see that these ridges just became a little bit more crisp, and they look a bit nicer, I would say. Next up, you can use a distort by noise to make to add some more detail. And what this will do is it will just kind of wiggle your terrain. So if you look from top side, you can kind of see the pattern that it makes, especially if we make our element size a bit larger and increase the amplitude as well to say 25. You can really start to see the specific patterns that this makes. I like to put this node in front of an erosion node because it just adds some nice detail that can then be eroded over. And that's what we're going to do now as well. I'm going to put down an erode node and use it to generate a bit more detail here and remove some of these harsher details here, because that's what the erosion node does. Setting it to roughly 12 frames of erosion should give us some nice detail. All right, there we go. So I'm going to turn off the visualization to really see the difference here. And if I click between the distort and the erode, we can see that it has kind of added some rivers here, or river-like structures. If we do turn on the visualize and compute the range, you can kind of see the result that it created under the hood. Without the visualize, this is not as visible. But I'd recommend playing around with this node. There's an incredible amount of parameters to play with. There's roughly 3 tabs that have some usable parameters, and there's just a lot going on here. So definitely play around with this to get what you want. For me, this works though, so let's use a height field output to output this to a height map. So software that might accept height fields are, or rather height maps, are Unreal. Unity has a height map importer as well now, and any other software really that accepts these height maps. We'll be looking at geometry later, so let's do this now. I'm just gonna set it to my export folder for height maps. There we go. And we're gonna want to set this to single channel, set our single channel to be the height. And I'm going to remap this, or rather auto remap it. You can manual remap it to be something that you want. I usually just auto remap it. Then we're going to set the type to be 16-bit fixed. This works best for Unreal, I found. So I'd recommend that. So just hit export here. And there we go, we've exported our map. Next up, we're gonna convert this to geometry, because some engines don't accept height field maps or height maps. So we're gonna have to use some geometry. Now, I personally don't like using this traditional convert height field because it ports all information that is on the height field. So if we open up our geometry spreadsheet, you can see that there's a lot of attributes now on this geometry. Instead, I'm going to be copying my grid from all the way up here. I'm going to paste it. And we're going to put down another point wrangle. And we're going to do the same operation that we did over here. We're going to transfer the height from this terrain here onto our points. This time though, we're going to use a volume sample function. So I'm going to create a float that represents our height. And this height is going to be equal to volume sample. The second input, we're going to sample the height volume at our current position, which is v at p. Putting this little v in here, or f or s, will declare the type to vex, so it's a little bit more stable. So I definitely recommend that. Next up, we're going to set our y again to be the height. And there we go, we've successfully transferred our height. Now we can start reducing this geometry. So let's put down a reduce node. This node is incredible at reducing geometry. And again, it has a lot of parameters, but we'll be using this percentage to keep for now. I'm going to put this down at about 30, and this generates some nice results. But what if you want to say, okay, well, I want my player to move through here, through this little river area here, but I do want to have some shots where I use this back of the terrain as well. Well, in that case, you can use the third input on the reduce node, which is the view geometry. So I'm just going to move this over here, use Alt drag to duplicate it, and I'm going to create a curve node. I'm going to set my viewport to top using the 2 button, and we're just going to use this curve and place a couple of points right through this this river or canyon area. The curve is still stuck on the ground right now, so I'm going to first resample it to add some detail. Probably set it to about 50 because our terrain is really big, still really dense. I think we can get away with setting it to 100. Yeah, that should be good. And next up, I'm going to set the polygon type to subdivision. So add some nice roundness to the polygon. Next up, I'm going to use a race up to project this curve onto our terrain. So let's set our direction to vector. I'm going to delete the channels here and set the y value to 1. So the curve looks up and finds a height value. And as you can see, it just snapped to our terrain. I'm going to move it up a little more because I don't want it to be stuck in the terrain in some areas. That might cause some issues. So I'm just going to move it up a bit by, let's say, 200 meters. Next up, I'm going to plug this curve into our third input. There we go. Let's wait for it to process, and there we go. It's already done. And what this has done, as you can see, it has kept a lot of polygons in this area, but if we flip around, this has a lot less detail because it's not visible. So this is an incredibly useful feature on this polyreduce, as it enables you to keep the areas that you want and, well, reduce the areas that you don't want. Or at least you maybe want them to be in the game or whatever you're making, but you don't want them to be as visible as often or from a way further distance. So I'm going to add some normals because I'm not particularly happy with how some of these normals worked out. I'm gonna just create a normal node, set the normals to be points, and I'm gonna set the weighting method to face area. There we go. Now let's create a normal map for this thing, and what better tool to use than the game dev game baker. If you want this game baker tool, you just have to go to your game development toolset and update your toolset, and you'll be able to use this tool. It's an incredibly useful tool that can just create texture maps or a lot of different maps for you with the blink of an eye. So we'll be needing the normal map. I'm going to just disable the rest. And let's plug this into our high-res geometry. I'm going to add a couple of dots by alt-dragging my line here. And we're going to have to add some UVs as well. So I'm just going to use a project since it's a height map. Anyway, we won't need anything else. And I'm going to add this to the low poly as well. There we go. So if we now press 5 to view our UVs, yeah, this should work. All right. So I'm going to just open this map baker up, set its resolution to be, let's say, 248 by 248, and I'm going to only generate a normal map. Let's press the bake button. Let's change this folder to be textures. There we go, and hit the bake button. And this is going to work pretty fast. As you can see, that only took about 13 seconds, which is, considering the amount of polygons, well, that's pretty good, I would say. Let's export our FBX using a FBX ROP. Here we go. I'm going to put this down, set the output to be to a specific folder here. I'm going to just call it terrain.fbx. I'm going to hit the save to disk, and there we go. All right, so let's jump into Unreal. I'm just going to import my geometry. So I've created a simple shader here and just imported the terrain. Let's put that down by dragging it in. Here we go. And as you can see, the normal map seems to be doing its job pretty well. The lighting seems to not be helping out here, but yeah, the normal map does its job pretty well here. Now let's also import our terrain using Unreal's landscape system. So you can do that by going to modes and then landscape. And I'm just going to import from file and select my height map. Once we have this, we can just change our options as we want them and then just hit import. And there we go. So this height map or landscape is completely editable. So here right now I have a circle brush that will smooth things. So I can smooth the terrain if I want, but I'll leave that to you guys to figure out. Well, there it is, our terrain inside of Unreal. This has been Yona for Dokai. Thank you for watching.